Okay, so we're very happy to have the David Kaplan from the University of Washington visiting us. For those of you who don't know, David's work has touched on all sorts of things, from lattice fermions to baryogenesis to solutions to the hierarchy problem I was making a list in my mind, I'm forgetting other things, nuclear physics to things that he's going to tell us about today. I'll also tell you, though, that came to know David when I was a postdoc in Seattle, and he had a strange obsession with the desire to propagate coin dollars into circulation. And so he tried to pay me back once with a bunch of these, and he chased me down the hallway, hurling rolls of dollar coins at me. So he's a really interesting guy to talk to, but just be careful.
I would have dusted off some of my story about you. Okay, so my interest here is in trying to understand connections between condensed matter physics and particle physics. There's a long history of very useful cross-pollination. For example, Dirac's work on antimatter gave the condensed matter physicists their idea of particles and holes, without which transistors would have been impossible. And then probably the most transformative theory of the 20th century in terms of long-lasting effects was the BCS theory of superconductivity, which gave particle physics the whole concept of spontaneous symmetry breaking for global symmetries, the Higgs mechanism, confinement. It gave us topological defects with vortices. Just about everything you need for the standard model that's not in QED comes from the theory of superconductivity. So one of the main topics of research in condensed matter physics for the past 40 years has been, since the discovery of the integer quantum Hall effect, has been, goes under the name now of topological superconductors and insulators. And I discovered maybe only 10 years ago that stuff that I've been doing on the lattice for lattice QCD back in the 90s was actually working with topological insulators. It's just that the language hadn't percolated back into particle physics, so I didn't know the connection. And I didn't realize that I was making a model of an integer quantum Hall effect. So I decided I'd try to learn a little bit more about it and try to see if there are other ways that the two fields can cross-pollinate. This is in part because the ideas really have been developed in parallel in particle physics and condensed matter physics, and with very little talking between the fields. And so the question goes both ways. Is there anything that condensed matter physicists could teach particle physics? Is there anything that particle physics could teach condensed matter physics? And I don't want to claim that this is anywhere near as rich a subject as superconductivity, but there are a couple different ways which go both directions that I will mention in my talk. So the start of the story is the integer quantum Hall effect, where you plot the transverse resistivity, which is just the Y voltage over the X current. And you see as a function of magnetic field, you get this sort of weird step function.
Did you define your coordinates before I arrived, or?
This is the resistance.
No, but what's X, Y, and Z? B is in what direction, and X and Y?
Yeah, so I'm going to be actually doing the opposite for the particle. So what happens is you turn on electric field in this direction, or voltage, and you get a current going in this direction.
And the B, if it's there,
the magnetic field
is out. Good.
Out
So it's C. Thank
whatever.
you.
One or the other.
And you've got a left-handed coordinate system. Okay. No, I'm kidding.
Okay. So, and what you find is, so I'm not plotting this right. The subscripts are getting higher, and for some reason they plot the resistivity instead of the conductivity, because the reason why I would have done conductivity is because what von Klitzing found was that that the resistivity went like 1 over n. It's nicer to plot it the inverse of that, because then you can see that it's an integer. So that was the discovery, and the thing that's very noticeable about all of these flat plateaus where the resistivity doesn't change at all is you change the magnetic field. And that was explained finally with this paper by Fallis and collaborators, where he showed that there was a topological explanation for that. And integers that are independent of parameters in your theory are natural in when you discuss topology, such as, say, the Euler characteristic of a manifold. You can stretch it and pull it and so on, and the Euler characteristic doesn't change unless you rip the manifold. And then when you rip it, you go through a transition and you can change the Euler characteristic. You reglue it, and that's what's going on here. That's the idea. And the topology is not the type of topology we normally talk about in particle physics, because you're talking about a system that's a lattice. It's not a continuous manifold. There really isn't topology on a lattice. You don't have smooth manifolds. You can always, you can't really define when you're tearing it, for example. The topology is a momentum space. So if you have an infinite lattice, the momentum space is a torus, and it's continuous, and that is where the topology is. And I'll talk a bit more about that in particle physics language later. So this was the sort of first topological material that people discovered, and then they found that it's quite ubiquitous. There's a whole table there, which is very intimidating, and it will be a little less intimidating when I explain it. But part of the attraction in trying to understand it is because they've got all that structure there. Is there any way that this enters particle physics? Yeah, interesting. So throughout this, I'm actually going to be talking about free fermions, okay? And let's start with 0 + 1 dimensions. And you have some energy, and my theory might have some parameters. I'll call it G, some coupling constant. And you can have a bunch of different energy levels. And I'm going to assume that I've got an insulator, which means that the system is gapped. That's all it means, that there's an energy gap. And so you can have a bunch of levels like this and a bunch of levels down here too. And if you wanted to define an integer for this system that doesn't change as long as you don't remove the gap, a simple way you can come up with is number of negative energy states. Seems sort of trivial, but because you're saying by fiat, I'm only going to talk about gap systems, and then when I talk about gap systems, whenever I change the parameters of the theory, the number of negative energy states can't change because they'd have to cross 0, and then it's not gapped. But that is what they're talking about. That is the topology for the lowest dimension system. Now, you can imagine that you can go through a critical value of the coupling where, in fact, you do lose the gap. So when you do that, then you go from a gap system to another gap system, and the number of negative energy states has changed. And so this is called the topological phase transition. Now, the question then is that all there is? And the answer is no. There are ways that symmetries can constrain the system. There are symmetries can constrain whether or not, what happens when the levels are crossing. And so that's where all this structure is going to come from. So the symmetries that play a role are what we would call space-time symmetries. So for the condensed matter physicists, they talk about Hamiltonians. So they have a Hamiltonian, and it gets turned into its conjugate. And then they have P, and you're thinking that means parity, but no, we're in a mirror world here. This is particle-hole symmetry. So it is related to what we would call C, okay? And And it has probably P dagger HP is equal to negative H transpose. And then they have something which they call C, which we would call CT, and they call it chiral symmetry. And this really is like our chiral symmetry, because if you think about how we define T, we usually define C dagger gamma mu C is minus gamma mu transpose, and T dagger gamma mu T is plus gamma mu transpose, and therefore you can define T is equal to gamma 5 C if there's a gamma 5 in your dimension, in which case CT is gamma 5. So when there is a gamma 5, but we actually agree that CT looks like gamma 5, and so this is, so they define this, it's sometimes called S, which is sublattice symmetry. And so if we use S, it's S dagger H S equals minus H. So this would be like our gamma 5, H gamma 5 is minus H. Or better yet, if you define your chiral symmetry to be, if you work on a chiral basis, then it tells you that H is this form. And they call that sublattice symmetry because you've got two sublattices which interact with each other, which means that H has to be off diagonal. So how do these symmetries affect things? Well, if you have no symmetries in the model, you could obviously have a picture like that. Suppose you had a T symmetry. And let's suppose that T is symmetric. Well, then I could choose a basis where T equals 1. And it will clearly not affect the spectrum at all. Okay? So when I have a T symmetry which is symmetric, I'll get the same sort of picture. And I can have any number of level crossings like that. But suppose I have T antisymmetric. Now, because of the symmetry here, if H psi n, lambda n psi n, I can define chi n, which is defined to be T psi n star, and then you find that H chi n is equal to T dagger H T psi n star, which is equal to T H star psi n star, which is equal to lambda n T psi n star. So lambda diagonalized H are real. And so you see that chi n is also an eigenstate of the Hamiltonian with the same eigenvalue. Now, you have to ask, well, maybe it's the same state, but it's not, because if I look at chi n psi n, this would be identical. If you're in some dimension, this would look like chi n, this would look like psi n transpose T dagger chi n. Okay, because I used the fact that chi was equal to T psi n star. And so I have a psi n and a psi n transpose, and I have an anti-symmetric matrix in there, so this equals 0. And so that tells you that the states are orthogonal to each other. And so in this case, you can't have the above picture there. If you have some level crossings, you have to have 2 at a time, because all the lines are doubly degenerate. And so now the number of negative energy states will be, the transitions will involve even integers, not just integers. So what happens then is you classify all your different Hamiltonians according to these 3 symmetries. And you can have T equals 0, which means no symmetry, plus, which means T transpose equals T, or minus, that T transpose equals minus T. Same thing with the particle hole symmetry. And this gives you 9 possibilities. And then there's a 10th, which is that you don't have P or T symmetries, but you do have S product, so what we call CT symmetry. And so then you can classify your different types of materials by these 3. Is there a pointer? Yes. These 3 symmetries, either you don't have it, you have it in. These series have no T symmetry. These have symmetric T, no T, anti-symmetric T, no T, symmetric. Same for P. And then if you have T and P, you automatically have S, but you can have a system with no T, no P, and you do have S symmetry. So that gives you your 10 classes, and they give them names that come from random matrix theory. I don't know what the origin of those names are.
And why is S without any pluses and minuses?
Because it doesn't matter. You can always diagonalize gamma 5, so it's always not.
David, why can't there be, I mean, if we're doing lattice systems, you know, of course I have
Sorry,
to, if I'm doing lattice systems, since it's a condensed matter issue, why can't I have further symmetries, which are discrete lattice symmetries?
You can have other symmetries. Well, an obvious one is flavor symmetry, right? But
Yeah.
flavor symmetries are not interesting because you can always put the H in block diagonal form where every block only involves all the particles that are in the same representation. And then that block behaves like a one particle system. You don't, flavor, if it's a spin 3 under an SU2, the spin 3 just goes off on the side and doesn't affect. So every one of those level crossings would be threefold degenerate, but it's a trivial 3.
Oh, okay.
As for parity symmetry, I think, well, from a particle physics point of view, CT always comes along with P symmetry because of the CPT theorem. In general, condensed matter physicists don't want to assume that their samples are very simple and reflective, and they want dirt and disorder and things like that.
But what about all the crystal groups, for example?
What?
If your material has some, if it's a cubic lattice or a rectangular lattice, you have various crystal groups that change.
Right, you do. Yeah, I don't think they want to include those just the way they're not including angular momentum or anything like that. I don't know all the, I'm not a condensed matter physicist, so that you're going beyond what I know. But I think, again, H just goes to block diagonal form, and then you just get, some copies of the same representation under the crystal group, but it doesn't affect the degeneracy of the eigenvalues beyond that.
There are some refined classification of topological phases where you take into account this crystal. I don't think it's always true that you can factorize them. There are some interesting topological phases that comes when they combine in a trivial way.
Is that like when we generalize charge conjugation symmetry?
Yeah.
Yeah, that's.
Okay, then one caveat then, suppose you ask what happens if you just have, sorry, so I should say that the case where I had no symmetry, this is what is called the A class. And so you would expect that you could have any integer you want to classify the state. And so when you look on the A class, and you look at 0 plus 1 dimensions, you see a Z there, which tells you that the states are classified by all the integers. If you take the case where you have a T symmetry and it's anti-symmetric, so I have T symmetry but no C symmetry, I'm here, and now it tells you that the lines are doubly degenerate. You change the numbers by 2. Now, in here I had T symmetry, but it was symmetric and it didn't make any difference from no symmetry, so I expect a Z. So if you look at plus 0, 0, you get a Z again.
Are you still talking about 0+1 dimensions, or when you're talking about lattices and whatnot, I thought maybe you generalized to 3 dimensions?
Right now, it's not a lattice, it's just a point in time. It's a quantum mechanical system with no space. That's where it's easy to talk about. I'll talk about the extended case in a particle physics language a little later. And then the thing that's a little bit confusing for a particle physicist is the P symmetry, because they use this, this is for the, it's applied to the superconducting case where they use the Bogoliubov-de Gennes formulation, which is treating Majorana fermions like Dirac fermions, you double count. Okay, and so it's like having a Majorana fermion with a Majorana mass, that's the superconducting order parameter, Briggs fermion number. And you have a particle hole symmetry, but in fact, the hole and the particle are the same creature. Okay, so the counting the number of crossings is a little bit confusing in that case for a particle physicist, but you have to remember that the particles and the holes are the same thing. So if I look at the D class, which was the 0 plus 0, which is, I've got a P symmetry, which is symmetric, then you really talk, if you know, in a particle physics language, I'm really talking about a Majorana fermion, which I can write as 2 Weyl fermions, so 2 copies of the same Weyl fermion. So if I had no mass, there would be the dispersion relation. I can think of it as a Dirac particle by pretending this is an independent degree of freedom, and then it looks like I have this particle hole symmetry, but I'm lying because there really aren't this double degrees of freedom in there. So in fact, the only symmetry that you can, when you have a Majorana mass, because particles and holes are the same, the only thing you can use to classify the ground state is the fermion parity. Is the ground state a fermion or a boson? And so when you see this class then, this D class, and I go to 0 plus 1 dimensions, I get a Z2. And that just tells you that the ground state's either a boson or a fermion. Now, suppose we say, okay, let's look at a relativistic system. Let's take the simplest thing, which is say a massive Dirac fermion. In equals 1 dimensions. And we know that it's a little tricky finding out whether you have those matrices or not and what their symmetries are. You can, it's all SON algebra, and what you find is if you take, okay, I should say that in particle theory, one thing that's a little confusing is that we take psi goes to C psi bar transpose under charge conjugation. Well, in condensed matter physics, they take psi goes to P psi star. So there's the difference is the gamma 0. And so what you find is that if C transpose equals plus or minus C, that implies that P transpose equals minus or plus P. So that C will have the opposite symmetry of what the condensed matter physicists call the symmetry of particle hole. So now you go do your gamma matrix algebra. If you look at T and C as a function of dimension, you get 0, 1, 2. You find plus 0, minus 0, plus, and this 0, minus 0, plus. And there's no point going on because the SO groups repeat every 8. And if you now read off this, remember to flip the signs over here to get to compare with condensed matter physics and read off what you've got on that table, you find that the Dirac fermions are all of these guys. And so on. All the Z's up that diagonal. And now you realize that, at least in this case, this periodic table is the familiar periodicity mod 8 of the SO groups. It's deeper than that, though, because if you go to a math encyclopedia and you look at homotopy groups, you'll see the same periodicity there, and there it's called Bott periodicity. So this eightfold periodicity appears everywhere. And when I talk about one of the possible applications to particle physics, I'm going to suggest it's not completely outlandish to think that the number of particles in one family, being 16, a multiple of 8, is not totally random. It could be because of the same periodicity. And I'll talk about that in a moment.
Isn't that the same statement that Clifford algebras? Isn't that the same statement that Clifford algebras also have this periodicity, mod 8 periodicity?
I'm sorry, okay.
Isn't that the same as Clifford algebras also having the same mod 8 periodicity?
Which is?
Clifford algebras.
This is the same column matrices, representations,
Yeah.
spin representations, up by so
Yeah.
It's the same story.
So one thing that is ubiquitous about topological insulators and superconductors is that when you have you take a system in two different topological phases and you put it next to the same system but in a different phase, then you find that there is a massless edge state. And the reason is because, again, with this quantum mechanics picture, if I have a set of states like that, and then on the other side I've got two states down that are negative, then there must have been one that crosses as I traverse from one side to the other. And so at the boundary, I'm going to find that there is a state. The theory has to go gapless. So there's a correspondence between the different numbers of edge states you can have and the different number of topological phases you can have, because if you have any two different topological phases, there has to be an edge state. So it's actually easier than doing homotopy groups is to just look at your system and ask how many edge states you can have. So edge states were discovered in particle physics in the mid-70s when Jakib and Rossi? Revy? I forget which. There are a bunch of papers by those by different combinations of this.
So one very nice question.
I'm sorry?
So very nice question. So you want the level crossing because you have different number of the edge levels for fit.
Yeah.
Why does it need to be topological? Because since based on your claim, you only need a different number of energy states.
I'm sorry?
I mean, based on your claim, why does it need to be topological? Because since if we only want the level crossing, then what we need is only the different number of the states on the basis.
So usually there's got to be a reason for there to be a massless particle, and so what I'm going to use this as a diagnostic. If you find a massless particle, it's probably there because you're at the boundary between two different topological phases. It's just that in particle physics, you didn't normally recognize these things as topological phases, and so that's what I'm going to talk a little bit about, how you can see that. So, Jakib and, was it, sorry?
Revy.
Awesome. So, looked at this equation, and Dirac equation, and now you just say, let's look in 2+1 dimensions. So I have t, x, and y, and let me suppose that m is a function of y, which looks like some sort of function of change of sign. And then you can immediately see that if I take I do mostly minus, sorry. So let me take say gamma 0 equals sigma 1 and gamma 1. So gamma t is sigma 1, gamma x is sigma 2, gamma y is sigma 3, and then you look at the y part of this equation, you get the, sorry, I want y's here. Then you get that minus sigma 3 dy minus m of y let's solve this equation. And you find then that you get two different solutions. You get, I can have an arbitrary function of x and t with an upper component times e to the minus integral y m of y prime dy prime. Or I could have, let's call it x plus, I can have 0 x minus of x and t times e to the plus integral 0 y m of y prime dy prime. Now, so normally if the mass is constant, these solutions are not good because they're not normalizable. But if the mass has this shape, this is a good one because it's this has a nice normalizable form. It looks like that. And this is bad because it has an unnormalizable form, looks like that. It exponentially grows away from the defect. And so what they discovered was that this is sort of cool system is that not only do you get a massless particle here, which you might think is plausible because the mass does go to 0 there, but it's not 0 right off the wall, so you wouldn't necessarily get a massless particle, but you do, but you only get one chirality in the sense that if I plug this into my action and I integrate over y, well, I expand my psi in terms of modes, eigenstates of the Dirac operator, for example. There will be one mode which I can stick, which will have this form, and if I stick it in, this one, if I stick it in, I will get integral dt dx integral, times chi bar I d slash 2 means this is just t and x. Where I integrated over the transverse wave function, and so it looks like a massless particle that lives on the boundary at y equals 0. And of course, if I expand psi modes, there will be plus massive modes. And from the 1+1 dimensional point of view, which are not localized. But we wouldn't normally integrate over y for those. Okay, so what's actually going on, which was not realized at the time, is that the theory with positive and negative mass are in different topological phases. And what you've done is you've tried to glue them together and you're forced to get a massless mode. How do we see topology in this quantum field theory? It's obviously not very easy to count negative energy modes and stuff like that. Well, there's a very useful paper by Kaplan and Harvey in '84. They were interested in addressing the question of how does, so before string theorists did string theory, they were doing anomalies. That was right up to the moment when Green and Short showed the anomaly cancellation in string theory, and they all went off and did string theory. But before then, it was all anomalies, and there was a very formal and difficult to understand paper by Zunino that talked about how anomalies in different dimensions were related to each other. And it was all in the language of forms, and it was not very physical. So Kaplan and Harvey decided they wanted to create a physical model to see how that worked. And so they looked at this 2+1 dimensional Dirac fermion. With the domain wall, which is what we call a mass profile like that. So you have a system like this. This is, in my perverse notation, this is x and this is y. And so we have this chiral mode that lives along this domain wall and moves in one direction because a chiral mode only moves in one direction in 1+1. Let me just say one thing, which is that if I had taken their model and added n flavors, I could have n up to n zero modes if I wanted, if I had all the signs have the same type of step function. So this is a theory where if you say that the number of zero modes, that there's a zero mode between any two phases, the fact that I can have any number of zero modes means that I have an infinite number of different topological phases. And so this theory would have to have a topological quantum number z, and we're in 2 plus 1, and we've got this case here, and you can check that this is a theory that does not have a T symmetry, but does have a particle hole symmetry, and a charge conjugation symmetry, the Dirac fermion 2 plus 1. Why doesn't it have a T symmetry? Under T, m psi bar psi goes to minus m psi bar psi. So the mass is T odd. It's also parity odd. And C even. So they said, well, there's something very confusing here, because if I look at this 1 plus 1 dimensional theory, I've got a dispersion relation that looks like that. And I know that if I fill the negative energy states and I turn an electric field on, then these states start marching up here, and the theory is anomalous. I shouldn't be able to gauge it. But you know that the 2 plus 1 dimensional theory doesn't have any gauge anomalies, so it should be fine. And so they said, well, what's going on here? Well, they said, let's integrate out the heavy bulk modes. And let's keep our photons in there. They're giving us our electric field. And there's one very special operator you get, which is this operator here. It's the Chern-Simons term. It's got a coefficient that's got e squared over number of pi's. And the way it depends on the mass, well, if you look at this, you see because of the epsilon tensor, this is T odd. So it has to be proportional to the mass of the fermion. So there's a mass here, because that breaks T symmetry, it's T odd. But if you look at the dimensions, this is dimension 3, we're in 3 dimensions, so the coefficient has to be dimensionless. And so you put in absolute value there. I'm working at bunny units where E is dimensionless. It's better to put the E in front of the F squared term, in which case you just get a 1. So you get an M over absolute value of M, and it's easy to see how that arises. It just basically comes from this integral. So they said, okay, so you get this Chern-Simons term, but now they're going to sort of fudge this and not work with a constant mass, but replace this with that mass, which means that this is now a set function. And if you then differentiate your effective action with respect to the gauge field, you find that it goes like m over, it looks like epsilon of y, 1 over 4 pi, epsilon u I j, e I a j. I'm going to put the e squared back. I'm sorry about the dimensions, but it's confusing otherwise. And this is just, so now if you look at jy, the perpendicular current, I'm sorry, I got my y and x's mixed up. You find that you get e squared over 4 pi epsilon ij, epsilon 2 pi epsilon ij fij, where fij is these indices are over time and x. And there's this epsilon of y out in front, which means that if I calculate the divergence of the current, the derivative with respect to y is going to hit that and give me a delta function and tell me that there is a divergence for the current at the wall, which is proportional to the electric field in the x direction. And when you match this coefficient up with that, with the anomaly here, it maps it perfectly. Now, they sort of messed up. Why did they mess up? They say in there, this is sort of like the Hall effect. They say you turn on an electric field and the current goes perpendicular to it. They should have said, this is exactly the quantum Hall effect, and look, you can do it without B fields. Which is, because there's no B field in here, okay? And if they had said that, they would have preempted Haldane's Nobel Prize winning paper by 4 years. Why did they not recognize that this was the quantum Hall effect? Well, first of all, this is one case where physicists, the particle physics units got them in trouble. If I want to calculate Rxy, and that'll be my voltage, that'll be I got X and Y reversed, it's EX over IY, okay? You can calculate it and you'll get this 2 pi over E squared. And the problem is they didn't realize that 2 pi is H. We said H bar to 1, therefore 2 pi is H. So first of all, they missed the fact that their current was in units of the von Kutzing quantized resistance. But there are a couple other problems. One is they did not recognize that there was any topology. And one reason they missed that is this diagram looks like it's nice and convergent. They didn't bother putting in a regulator. They found half of the current comes from one side, half from the other. If they put in a regulator, because heavy particles don't decouple, let's suppose they put a poly-Villars term in here, you'd have to add a lambda over absolute value lambda, where that is the poly-Villars mass. Now that is a constant. You don't want zero modes in the poly-Villars field. And so it doesn't affect the divergence, so it doesn't affect their anomaly argument. But it does give you a current which adds on one side and subtracts on the other. And so all the current comes from one side. Now it starts looking a bit more like the experimental system that the condensed matter physicists are looking at. But more importantly, when you put in a poly-Villars term, by regulating the system, you're compactifying momentum space. You don't get any topology momentum space until you compactify it.
So can you explain that point? Why does the poly-Villars regulator...
Again, Mr. Glauber, sorry.
Sorry, why does the poly-Villars regulator compactify momentum space? Can you explain that?
Why does it
Compactify momentum space, why?
It's basically replacing your propagator, your fermion operator by d slash over d slash plus m in Minkowski spacetime. And that means that the propagator goes to a constant for large momentum.
You're telling me if I go to p goes to infinity in any direction, this just goes to some
Right,
constant.
in fact, I'll talk about this later, but yeah, I could write this. So if I'm in Euclidean spacetime, where I can write this as 1/2 1 plus d slash minus lambda over d slash plus lambda. And since d slash is anti-Hermitian, this is a unitary matrix. Okay, and so the eigenvalues of d slash, the unregulated theory, live on the imaginary axis, but the eigenvalues of your regulated theory live on the circle. And so you compactify it.
Okay, thank you.
So, but the fundamental reason, again, that they did not recognize they have the integer quantum Hall effect is because there's no knob in here to make the current jump. So you didn't see the steps. So that's why they didn't think of it. Now, I got excited about this paper in the late 80s because it gave a chiral fermion here, but the fundamental theory had no chirality. And that was something that sounded like it'd be really good for the lattice, because the lattice had always struggled to simulate chiral fermions. And chirality is very important for understanding QCD. If you want to have light pions, if you want to avoid mixing between operators of different chiral properties, with the mixing, it's very hard to do weak matrix elements, for example. So this looked like an interesting thing. But more than that, the standard model is a chiral gauge theory, and unless you have chirality in the lattice, you'll never be able to come up with a nonperturbative regulator for the standard model. So that was a motivation for me to say, oh, the fundamental theory doesn't need chirality to have chiral fermions in it. Maybe we could do that on a lattice. So why does a lattice have a problem with chirality? Well, if you put in a naive fermion, a vial fermion like this, you put it on a lattice, well, it's the momentum space is a torus, so the thing's just going to come down again and be periodic. And so here you have your right-handed vial fermion, but over here you have a left-handed vial fermion. So you automatically get just from the periodicity of the lattice, you get a vector-like fermion, even if you try to write down the action of a vial fermion. So, but here what you do now is if you want to take a infinite lattice, of course for real computations you'll have to take a finite lattice, and you take a mass function that goes like this across this boundary here, and you just write down the lattice derivative. I'm going to work in Euclidean spacetime, no i's there, and you put this down where d mu psi of x is psi of x plus mu hat minus psi of x minus mu hat over twice the lattice spacing. If you do this, it doesn't work because you get doublers. You get you don't get one Dirac fermion on the lattice, you get 16 or 32 if you're working in 5 dimensions. So even if you have an m of x5 here, it doesn't work. But then you just have to do what Wilson did, is add a mass term, I mean a radiant term, so minus del squared, where this is the lattice Laplacian, and this gets rid of the high frequency mode, so you end up getting something that looks like a Dirac fermion, and now if you put this domain wall mass in it, you find that indeed you get a chiral fermion here. You get a left-handed vial fermion, say, right-handed vial fermion. Now, if you want to do a real computation, you have to have a finite lattice, and so there'll be an anti-domain wall over here, and here you'll get a left-handed one. So this does not work for chiral gauge series, but it does work for QCD. If I now, these are exponentially located on the domain walls, if this is reasonably far apart, and I have my gluon fields be constant over the extra dimension and only propagate in that dimension, then you've got a way of doing QCD with light, massless, essentially massless chiral fermions. So that's, I was interested in that. My main interest is to do chiral gauge theory, but I couldn't get rid of the modes on one side. So, but it was useful for QCD. But then I asked this incredibly talented graduate student I had at the time to look what happens if you change the coupling there relative to the mass. And oh, Martin. And he found out that that the number and chirality of the modes here changed abruptly. And so what you find is that if you take m over r from 0 to 2, or 2 to 4, or 4 to 6, and so on, what you find is you get one left-handed in this range, 4 right-handed, 6 left-handed, 4 back down to 4 right-handed, and 1 left-handed, and then nothing. So depending on the relative size of these couplings, you get this many modes there, and it has to do with corners of the Fermi zone, which is not so interesting to me. But the fact that this could change abruptly means that the current flowing between the walls must be changing abruptly, and this is the integer quantum Hall effect. It's just not going up to this infinite stairway, but it is a stairway which is completely flat in between those choices of parameters. And so in the modern language, this is where topological phase transition happens. Well, what is happening at these special values of m over r is that the gap goes away in the bulk. So this looks exactly what's going on in a topological phase transition. But at the time, this was very confusing, and I had a skeptical colleague tell me, or not a colleague at my university, but a collaborator tell me that this must spell trouble for the model, because if the number of modes is changing and the chiral is changing, the current has to suddenly change. And how could that be? Because the current was computed by computing a Feynman diagram. Okay, and this Feynman diagram depends on the mass of the fermion and the Laplacian coupling. And how in the world can a Feynman diagram give you integers that change discontinuously with the parameters? So I was depressed, and I really didn't want to compute this because the propagators for Wilson fermions are nasty, and the gauge couplings are nasty. So I decided to simplify it.
Can I ask a question?
Yeah.
Are you now still in the 2-dimension, or are you in the 4-dimension?
I'm sorry, what?
Are you still in the 2-dimension, 2 plus 1 dimension, or are you in the 4 plus 1 dimension?
My hearing's terrible. I can't
Are
hear
you
the
still in the
math.
2 plus 1 dimension, or are you talking about 4 plus 1 dimension?
So this could either be 2 plus 1 or 5. Yeah, I'm in Euclidean space. It could either be 3 dimensions bulk with 2-dimensional surface, or 1 plus 1.
But when you mentioned the application to the chiral gauge
Oh,
theory,
here I was doing it for
4 plus 1, I see.
Yeah, it goes through the corners of the Brillouin zone. You just
Yes.
count corners. So in 3 to 2 would be 1, 3, 3, 1. I guess this is the Hughes G somebody model. So this was in the early 90s, and so the question is how to compute this. Well, so if you look at this diagram here, and you say that this is a propagator, S of Q, this is S of Q plus P, and use the word identity for this coupling here, which is just a fancy way of saying that gauge fields come in packaged in covariant derivatives, so the momentum dependence of the propagator knows about the gauge coupling. And you say, okay, I want to pull out the piece that's proportional to ADA. Well, that means I have to pull out I have to Taylor expand this to first order in P, because P is that derivative there, and then set P to 0. And you do this, and you end up massaging this, and you get something that looks like this. You get 3 powers of S ds inverse. So these are derivatives with respect to momentum. 2 of them come from the fact that I've got 2 vertices. The third comes from the fact that I have to Taylor expand this to linear order in P. And lo and behold, this looks very much like a winding number calculation. And to see what it is, if you just say that S of P inverse looks like A of P, let me do it in 2 plus 1, or you find, well, in general, you'll get this. That's sort of a generic form for an inverse propagator. And I can divide and multiply by the norm of this thing. This here, let's do it in 2 plus 1, where these are just Pauli matrices. This is just an SU2 matrix. And this factor out in front, it turns out does not contribute to this combination with the epsilon tensor. It just drops out. As long as the square root doesn't vanish. Where does it vanish? Well, it vanishes when the bulk goes gapless. So let's say it doesn't vanish. Now, what this is a map from momentum space, which is T3 or T5, to SU2, which is equal to S3. And this is the winding number of the map, and the coefficient gives me the winding number, and lo and behold, it can jump when this vanishes, which is at the magic values of m of r equals 2, 4, so on, and you can calculate the jumps and figure out what it is, and it matches this perfectly. So this is the topology. It's topology in momentum space, and it actually matches on nicely to the Thales calculation from the early 80s. Okay, this is taking longer than I expected, so let me get to
Can I ask
some
a question?
punchlines. Yeah.
What is this Rn continuum? You said, del square is the lattice Laplacian, right? This calculation of Feynman diagram is in continuum.
So this, yeah,
Yeah, what is R in the continuum?
R is just a coupling constant.
No, but in continuum, like
Oh,
in the continuum model, when you compute this Feynman diagram,
yeah.
where does R enter?
Okay, so the actual form for this, for the Wilson fermion, is that A is equal to minus M plus sum of I equals 1 to D of 1 minus cos PI, and B is equal to sine of this, sorry, and there's an R on it. Or R over 2, okay. Okay, so the first place where there could be some cross-pollination is if you want to get rid of, you want to simulate the standard model, you have to get rid of, one scenario is that you put the standard model family on one wall and mirror fermions on the other wall, mirror being exactly the same quantum numbers except for the opposite handedness. And then you find some way to make, oh, let me put left-handed here and right-handed there. And you want to make these heavy. But how do you do that? You know that you cannot make them heavy by just writing down a mass term. That violates gauge invariance. You know that you can't, you could put in a Higgs, but then it would give the W mass 2, and we know that it's ruled out to have mirror fermions up at a few hundred GeV, so that's not good. So how can you make these heavy? Well, back in the mid-80s, Eichen and Prestel suggested you put in 4 fermion operators for the mirrors, and that if the anomalies were canceled properly to allow a completely gapped system, you could use the strong interactions here to make all these mirrors heavy and get rid of them without actually writing down bilinear. You have only 4 fermion operators. They didn't do it in the context of domain walls. They suggested for SU5, you could have a 5 plus 10 bar left-handed field plus a 5 bar plus 10. This is, I'm doing it language, they're all left-handed, but these have opposite quantum numbers. Then you put in an operator that looks like G 10, 10, 10, 5 bar. That allows for some sort of interaction. You make G strong, and they hoped that this would gap the system. But it's a hope, it's a strong coupling system. We don't know if that happens. So it was interesting, but it didn't really go anywhere. It's very hard to simulate something like that. So the question was, maybe this could happen here. And the thing that's sort of interesting is that in low dimensions, there is a condensed matter example where you can encapsulate that this actually is possible. So I'll show you that. And this is something that I'm not directly working on now, but there are a number of groups that have been working on this. Namely, Xiaogang Wen, Yuan Wang, Senki, a bunch of people are doing this. And it's based on 2 different papers, well, a paper by Kitaev, and then 10 years later, a paper by Kitaev and Topological, where they looked at a model which in quantum field theory language is a 2-component Majorana fermion in 1 plus 1 dimensions with the domain wall. Or it's simpler for me to talk about domain walls. It could be just a wire with a boundary with the appropriate boundary conditions. But just think of it as a domain wall. So the Lagrangian is psi eta transpose C I d slash minus m eta. C is the charge conjugation matrix. And you can put in a step function. And you can find that you get 0 modes. One component edge states. So the excitement of today's original paper is that you can actually realize this in an electron system. Why is that interesting? Well, if you have eta is equal to e to the minus log of m x times chi of t 0, that's your edge state. Well, chi squared equals 0. It's a Majorana fermion. It's a real fermion. You can't write ladder operators for it. There's no Hilbert space for it. Try, you could define chi acting on this state to be 1, but there's no lowering operator. You can't. There's nothing you can do. So there's no Hilbert space for the system. You really need the edge state on the other end of the wire to make a Hilbert space. And if you made this out of electrons, that means there's half an electron here and half an electron there. And his idea was you could use these as qubits, because in order to destroy this qubit, you're going to have to do it at both ends of the wire at the same time. And since noise is typically localized, that idea was to use this for a stable way of doing quantum computation. But he then also had a separate question, which was, all of those classifications on that fancy table were for free fermions. The question was, what do interactions do? And so he said, let's suppose we have n of these particles. Who in this quantum dot at the end, we have n of these Majorana fields. And what keeps them massless? Well, it turns out this theory has a T symmetry. And a useful basis, it's that. Okay, so in fact, in that basis, you get something like this. It's choice of basis. But the important thing is not that what happens to chi. I don't remember whether it's plus or minus chi. It's one of the two. But the important thing is that if I were to write down a mass term, if I have chi1, chi2, and I want this to be a Hermitian, so these are real fields, hermiticity changes the order, Hermitian conjugation, and I get a minus sign when I go back, so I need an I here to make it Hermitian. And if there's an I there, the T reversal is going to conjugate that because it's anti-unitary and makes this odd. So masses are forbidden if you have T symmetry. So he said, well, let's look at four fermion interactions. So what we can do is we can make a Hilbert space if we have an even number. And these are the nice usual fermion anti-commutation relations. So if I have 2n Majorana modes, I've got n Dirac fermions living on massless Dirac fermions, and I can ask what happens if I write down a four fermion interaction. So let me try eta 1, eta 2, I'm sorry, chi1, chi2, something like that. Well, what happens? So one way of saying it is, I've got a nice way of understanding this is to say, let's go back to the chi's and remember that the chi's obey a Clifford algebra. And so I can represent them with as gamma matrices. So if I get n of them, I've got an SON algebra, and these could be represented as SON gamma matrices. And so this is a product of gamma matrices. And the question is whether I was able to gap the fermions becomes a question of whether the vacuum is unique or not. Because if I don't gap the fermions, then there are many different states that all have zero energy. So that becomes now an algebra question. If I take a string of gamma matrices, 4 gamma matrices, when can I have a unique lowest eigenvalue to that matrix? Well, it turns out that if you go back and you look at your SON groups and you look at the C and T matrices that you can define for them, they will often put constraints that your eigenvalues are doubly degenerate or quadruply degenerate. And so whenever that happens, you know you can never have a unique ground state. And you ask, well, what SONs can I have a unique ground state? It turns out there's only one for every 8, and namely SO8K. Which means that the number of fermions is 8K. It's a multiple of 8, and then you can gap all the fermions. So this was a surprise you could do it at all. That beautiful table does not say anything about interactions, but it tells you that you can, in fact, make that if you have 8 flavors, it's actually trivial. You can gap them all without breaking your T reversal symmetry. Now, this is really interesting then in the context of getting rid of those here. Unfortunately, 4 dimensions is much more complicated than 0 dimensions, and it becomes, it's harder to do non-perturbative calculations, but there's a lot of effort being done trying to figure out a theory where you can show that that can happen. So the question then is, does non-perturbative regulator for standard model tell us things we don't know about the standard model? It's sort of embarrassing we don't have a regulator, but you'd like to know that you can learn something new. And maybe one of the things is you can show, maybe you might be able to show that the number of fermions in a family has to be a multiple of 8. That might be sort of an interesting outcome. It's a very basic 8. It comes from the fact that your fundamental fermion, the simplest fermion you can have, basically different algorithm. And SON groups have this 8-fold repetition. But the last thing I want to mention, just to be really brief, it's what I'm actually working on right now, is the fact that there was some work done by Neuberger to say, well, can we ever describe the edge states without describing the bulk states? And he very cleverly was able to integrate all the bulk states and come up with an operator which describes the edge states and has all of the anomaly information encoded in it without referring to the bulk states at all. And as far as I can tell, this is something that the condensed matter physicists don't know about. And so for every one of those entries on this periodic table, you can construct one of these Neuberger operators in Euclidean spacetime, which will describe the motion of these and the coupling of these to gauge fields and other background fields without ever making mention to the bulk states. The problem is the way it's normally formulated. It's very nonlinear in time derivatives and difficult to bring back to Minkowski spacetime where condensed matter physics lives. But it seems like there's some tricks that allow you to do that. And so that's what I'm working on right now. And that would be the fertilization from particle physics back to condensed matter physics. And it was just, I figured it was too technical and too foreign a language to just launch into describing how that works. So we'll have to read my paper. Thank you. Sorry, Gold.
No, other questions?
So is there something interesting about that 1+1 case already, that one can do a chiral theory that one wouldn't have otherwise been able to do by adding the fermion?
No, because the 0 plus 1 dimensional theory doesn't have chirality. It's the even space-time dimensions that have chirality. So you'd like to do 2 plus 1 to 1 plus 1, but then already it gets much more complicated. It becomes a quantum field theory, and it's harder to think about how to do the calculation. What I am trying to do, and I got a bit stuck in it, I want to go back to it, is to take this very simple quantum mechanics model and ask, if I only had path integrals to use, how would I see this happen? And it's incredibly hard. The ground state, if you have eight Majoranas, you've got 4 Dirac fermions in it, so you can label your state as N1, N2, N4, where N is 0 or 1. And what this interact with the ground state is the linear combination of all empty and all full. Okay, I don't really know how to see in path integrals if that's going to be the ground state, and without doing an infinite number of diagrams, which is ridiculous because it's so simple to solve analytically in the quantum mechanics language.
There's a different perspective on this gapping the Majorana fermions, where you can directly study the the theory of two-dimensional massless Mariana fermions. And when you have 8 of them, you can construct the boundary condition to precisely correspond to.
Okay, I'll have to talk to you about.
That's the same boundary condition that Molasina and Witkowski studied
Okay, well, maybe
when they're trying to shed some light on this Kanaru and Cobb effect.
I'll see more about it.
I'll mention also that David's here for another
All next week.
all next week, and he's sitting right over there.
You're welcome to knock on my door.
Thank David again.